That is called as the electric flux line. So this is the electric flux line. Okay, so with an arrow. So rather than putting it as vectors. So if you join those vectors, then you form a line, and that is your electric flux line. Now you have also what is called as equipotential surface. I think we discussed about this. Equipotential surface is nothing but it's a surface, where any surface on which the potential is the same throughout is known as an equipotential surface. A surface on which the potential is same throughout is called an equipotential surface. And we talked about this when I mentioned that your electric field vector will always be perpendicular to the surface. So when the electric field vector is always perpendicular to the surface, this is an imaginary surface. So you have an electric field vector, and now you are trying to construct a surface in such a way that the electric field vector always is normal to that surface. It's almost normal to that surface. And that surface is called equipotential surface, because wherever you go on that equipotential surface, your electric field will be same and your potential will be the same. And if you want to look at how, so here, it's not so easy to find the equipotential surface. See how they are. So you can go to this, software, and then you can look at the equipotential surface. So we looked at the point chart, and I explained it to you. Its equipotential surface will be like a spherical shell. So if you want, you can go and you can see equipotentials. See, it will not. So this software will not give you a 3D view of the surface, but it will give you a 2D view of the surface. For example, it is only giving a slice of Z. That is, it is not considering in 3D, it is considering in 2D. So in the 2D, see, it's like a circle. So you can also take it X slice, it is also a circle. And you can also take its Y slice, it is also a circle. Now just try to construct these circles in 3 dimensions. So if you try to construct the circles in a 3 dimension, you will get a spherical shell. That is your equipotential surface. So it's easy for just a point charge, but as your charge distribution becomes, say complicated, then visualizing the equipotential surface becomes difficult. So for example, in this, so now we are here in our dipole. So in the dipole, so this is the electric field vector. See, this is in 2D. So this is the positive charge. This is the negative charge, 2D. So if you want to see it in 3D, this is how it looks like. See, in 3D. And what will be the equipotential surface for this one? You have to think about it. Difficult to visualize, but if you want, this is how they look like. And this is again in your Y slice. So that is, this is in the XZ plane. Then in the X slice, they look like this. And in Z slice, they look like this. So you have to construct a surface by joining all these three. Difficult, but with the simple, point charge, we have seen how to construct an equipotential surface and we know its properties. So the same property holds for the dipole. Okay, so let's now go back to our course. So we looked at the equipotential surface, and we also have equipotential lines. So equipotential lines is nothing but the slices that you are seeing. These are all equipotential lines. So this is the equipotential lines in this plane. This is the equipotential line in this plane. And this is the equipotential line in this plane. And if you put all these equipotential lines together, that gives you the equipotential surface. Okay. So now let's take the last section of our chapter number 4, which is the electrostatic energy and energy density. Now, any electrostatic vector field or magnetostatic vector field, they contain energy. Okay, that means they have energy within it, within their field. And that energy, we can find it by using this expression, which is WE is equal to half volume integral d bar dot E bar dV. So because it's a vector field, in order to find its energy, you have to first find in which volume you want to look at the energy. So therefore, if you identify that volume, then if you integrate your d bar dot E bar over that volume and then take half of it, that is called as the energy of that electrostatic field within that volume. Sometimes it's also good to use, rather than energy in joules, use energy density, which is joules per meter cube. That is normalized to the volume. And this is defined as small w. E is for electrostatic. So small WE is energy density. It is half epsilon E square. Okay, it is half epsilon E square, which is nothing but d square over 2 epsilon also. Okay? So when you convert electric field to the electric flux density. And this energy density, if you integrate over any volume, will give you the total energy in joules. So it is integral over V half epsilon E square, or integral over V d square over 2 epsilon, integrate over the volume. Now, because of the time constraint, it's difficult to go through the derivation of this one. But if you want, you can see it in the textbook, how it is derived. So I'm looking at this, the energy in joules, and then generalize, this is for the point charges, and then generalized to charge distribution. So for the Rhine charge, for the surface charge, for the volume charge. Okay, so this is our where it is. So yeah, so all these derivations. So this is the general expression, and from here, if we go and if we see, this is the expression. So the energy is half integral over V d bar dot E bar d. And this is common for any charge distribution, whether it is point, whether it is line, whether it is surface, whether it is volume. And then, some modified versions of this. These are the modified, which I have just not discussed. So it is half integral V epsilon E square dV, or you also define it as energy density, which is small we is half epsilon E square or d square over 2 epsilon. And to find W, it is integral over the energy density. So integral the energy density over the volume. And you have some of the examples you can look at these examples. Now let's look at the example that we have. It's a very simple example. We have an electrostatic field in rectangular coordinates, which is 5ax plus 2ay volts per meter. And we need to calculate the energy stored in a cube of side 2 meters centered at origin. So this is the electric field everywhere in free space. Now I have a small cube of 2 meters side, and it is centered at origin. And I want to see how much is the energy which is enclosed in this cube because of the electric field which is passing in the free space and passing through that cube. So first, energy density. So it is half epsilon E square. So E square is nothing but the magnitude of this. Small e is nothing but the magnitude. Not small e. The italicized E is the magnitude of this, and E square is the magnitude of this square. So that's why square and square root cancel, and you get 5 square plus 2 square. And this is your energy density. Now, what will be the energy which is enclosed by a cube, the energy which is enclosed by a cube of 2 meters is integral over the volume WE, small we dV. Now, if you see, our small we is a constant. So therefore, if it is this is a constant, then you can simply take it outside. So your capital WE will be small we integral over the volume dV. And what is the volume of this cube of side 2 meters? The volume is side cube. We know it, the side cube. This integral V dV will become the volume, which is nothing but the side cube. And again, I'm emphasizing here, this was only possible because my energy density was uniform. It's a constant. That's why you can easily take it out and replace integral V dV with the expression, because from schooling we know that the volume of a cube is side cube. But if it is not uniform, that means if it becomes a function of a spatial coordinates, then you cannot do this. This is wrong. This is wrong. You cannot do this. You have to keep it inside and then do the integration. Okay, I think there is one example on that. See, here, if I'm not mistaken, there is an example here. So please, go and have a look at this example. Okay, so this is the energy density, and this actually concludes our chapter 4. Now we are going to chapter 5. So in the chapter 5, we are looking at the electric field in matter, and then we will look at the boundary conditions, and we will define the conduction current, convection current, and other things. Okay, so let's start. So now, again, all these are mentioned in our textbook. So my notes are just summarizing. So we are looking at the properties of the material. Okay, so we look at the conduction, convection currents, and then I'm talking about this one, the conductors and the expressions and all these things. So electric field in matter. So a matter, at least within the umbrella of electromagnetics, we divide it into either conducting or non-conducting. That is non-insulating, which is nothing but your conductor, or insulator, which is nothing but your dielectric. So matter, they're divided into two, either dielectric materials or conducting materials. Now, how electric field will affect these two types of matter is what I am summarizing here. If you see here, this is what I am summarizing. Now, if you have a conductor, so this is your conductor, and this is your dielectric or your insulator. Now, in a conductor, we know it very well. We have large number of free electrons, right? So we have large number of free electrons in the conduction band. This is the property of the conductor. Whereas in insulator, we don't have large number of free electrons in the conduction band. And also those electrons which are in the valence band, which are in the orbitals, they are all very well, how should I put it? They are very well attracted by the nucleus. So it's not so easy to pull the electrons from these orbitals and make it as free electrons. That's why they are dielectric or insulators. Now, when I keep a conductor, okay, so conductor, you can think of anything, maybe say a metallic rod or a metallic ball. So you are placing that metallic ball in a room which is filled with electric field. Then what will happen to this metallic ball? So if you see here, this is what happens. So if the electric field in the with the influence of this electric field, suppose your electric field is going in this direction, then what will happen is the electrons will try to move in the other direction. They will try to move in the other direction. So the free electrons or the conducting electrons, they will try to move in other direction. So negative charges move due to Coulomb's force, and these negative charges can move because they are not tightly held to the atom. So these are your conductors. So these negative ions are, sorry, these negative particles or electrons, they are experiencing a force because of this electric field. And that force is what? Pushing them. So if the electric field is going here, then the electrons are pushed in this way. Then in this case, what will happen? At one end of the conductor, okay, according to where the electric field is, at one end of the conductor, all these negative charges or our electrons will be accumulated. And then if the electrons are accumulated in these, then automatically the positive charges will be accumulated here. So in this case, what will happen is you have, yes, with the influence of electric field, there is a change in the distribution of the charges, but overall the net charge is zero, because in the distribution of charges, some charges came here, then some charges came here, but the overall, the number of negative charges and the number of positive charges are the same because it's a neutral conductor. So the number of negative charges and the number of positive charges are the same. Maybe before the electric field, the negative charges were, say, within the atom, or it, maybe they are in the valence band, or maybe some of them are in the conduction band. This is what happened. But now in this case, you can think that, all the electrons, maybe they have come out of the conduction, come out of the valence band, and they have become free electrons, and they have moved into, they have been pulled into one direction, and all the atoms which has the nucleus, which is the positive charges, they might have moved in the other direction. But overall, the net charge is the number of positive and the negative ions will be the same. So the net charge will be zero. There will be no net charge inside the conductor. So therefore, the charge density will be zero. Now what will happen is, because the negative charges are coming at one end and positive charges are coming at other end, this is again a property of electric field, because these negative and these positive charges, they will try to attract each other. So there will again be a force created between these two, right? Again, there will be a force created between these two. This is due to Coulomb's law. And that actually creates another electric field, which is called as the induced electric field. And this induced IND, this induced electric field direction will be from away from the positive and towards the negative. So this induced electric field direction is away from the positive and towards the negative, which is exactly opposite to the applied electric field, which is exactly opposite, as well as it will be exactly equal in magnitude. It will be opposite and it will be exactly equal in magnitude. And therefore, inside, what will happen? The total electric field inside the conductor will be the total E will be the induced electric field plus the electric field which is applied. So the electric field which is going inside the conductor, which is the applied electric field. And because of this applied electric field, you have separation of these charges. And this separation of charges is creating another induced electric field, which is equal in magnitude but opposite in direction. And therefore, the net electric field inside the conductor will be 0. So these are the two very important properties of a conductor. That if you have a conductor, just a conductor, which is placed in the vicinity of an electric field, and then if you go inside the conductor, there will be no electric field. Electric field will be 0. Okay. And please remember one thing. This is the case where the conductor is, neutral, where the conductor is neutral. Got it? Neutral. Now for the dielectric, because the dielectric doesn't have any free electrons, so these electrons are tightly bonded with your nucleus. So your nucleus is your positive charge, and your electrons which are in the orbital, particularly the valence electrons, they are tightly bonded. So that's why I'm showing the atom in this manner, minus and plus. Now, when the dielectric is, a dielectric material is now put under the influence of an applied electric field, electrostatic field, then what will happen? So it is very difficult to pull the electrons out of the atom. But what will happen is, because of this electric field, your negative electrons will try to move in this direction, and your positive nucleus will try to move in this direction. So because of the influence of electric field, the distance between these two under the neutral case, the distance between these two without electric field, without applying electric field, and with applying electric field will change. That means without applying electric field, if this is the distance, then see, if this is the distance, then by applying electric field, the distance will increase. That means from a circular orbital, it becomes an oval shape orbital. Because you are pulling, so the electrons are getting pulled by the influence of the applied electric field. So instead of going in circle, they are now, like pulled. So they are becoming like oval. So negative charges are only displaced with respect to positive charges. So only they are displaced. So if this is positive and this is negative, then in the influence of the electric field, so the negative will be moved and positive will be moved on this side. So instead of circle, it will become like an oval. But no current will be produced because there are no free electrons. So this is the property. No current is produced because the negative charges are tightly held to the atom and are thus only slightly displaced. But what will happen is this slight displacement creates what is called as dipoles, which we have studied in our previous class. A negative charge and a positive charge, they are held together with a small distance between them, d. But a dipole is created. Because here it was neutral, nothing was there. But here the distance has increased because of this influence. And because this distance has increased, this dipole will generate its own electric field. So that's why a number of dipoles are produced in the electric field and we in the dielectric material, and we say that the dielectric material is polarized. Okay, is polarized. And this polarized, we put it under the umbrella of what is called as polarization. And polarization is a vector. And this polarization is coming because of the electric field created by these dipoles. Okay, so there is a lot of physics inside this, but because of our course, time limitation and also our level, we will not go into the details. Okay, so this is the difference between the conductor and insulator. So remember here, sigma in our course is called as conductivity. So we know it very well that for conductors, the conductivity should be very, very high, but for insulators, it has to be very, very low. But here, the explanations that I gave you, these are the explanations for the ideal cases. So the ideal cases means perfect conductor. That is, your conductivity is infinite. And perfect insulator, that means your conductivity is 0. But remember, in our practical case, it's difficult to have these kind of materials. So although your insulator is there, but still it will have some conductivity, and your conductor is there, you will not get infinite conductance or conductivity. Nowadays, you have with the name superconductors are coming, which is very close to infinity, but still many materials, all the materials, they don't have infinite conductivity. Okay, so now let's go to the relative permittivity. Again, as I told you, permittivity is the property of a material, which we put it under the umbrella of epsilon. Now we are just going a little bit inside what is epsilon, but not too much, because again, only, we need to look at the expressions, but just remember the little bit of physics behind it, and that's it. So we are not going to go and look at all the derivations and other things, because in the book you have all the derivations, but unfortunately we will not be able to do the derivations. But we will just see, we will just take these expressions. That's it. Okay. So what is relative permittivity is epsilon, and it is actually made up of epsilon r and epsilon 0. That means any material, we are trying to represent its permittivity in terms of the permittivity of the free space, which is epsilon 0. So your permittivity of free space, you are multiplying it by another term, and you are getting the permittivity of your required material. And this term is called as relative permittivity. So this is permittivity of free space, epsilon 0. This is 0 automatically. It means that it's for the free space. And epsilon r is the relative permittivity. And then epsilon is the permittivity of any material. So in this case, what will be the relative permittivity of free space? Yes,
1.
tell me.
1.
Yes, 1. So therefore, the relative permittivity of the free space is 1. Whereas for other materials, it will change. So the relative permittivity is epsilon over epsilon 0. And the relative permittivity epsilon r in our electrical engineering, we also name it as a dielectric constant. Very, very common. It is called as the dielectric constant of a medium. And how we can get this relative permittivity? Relative permittivity is equal to 1 plus chi e. And then chi e is called as electric susceptibility. It is called as electric susceptibility. That means it's a quantity of a material. And this quantity is telling us that how good your material gets affected by the application of an external electrostatic field or an external electric field, how your material will get influenced because of this electrostatic field. That is put under what is called as electric susceptibility. But we will not go into the detail of that. So I just explained you a little bit of physics, that or the definition of chi e. So that is called as electric susceptibility. And add 1 to it, you will get the relative permittivity. And therefore, now we know D bar. D bar is epsilon E bar. So epsilon, I'm now replacing it with this our expression, which is epsilon or epsilon naught. Epsilon naught is as it is. Epsilon R, we just know said that it is 1 plus chi E. So epsilon naught times 1 plus chi E times E bar. Now open the brackets. It is epsilon naught E bar plus epsilon naught chi E E bar. And this epsilon naught E bar as it is. This epsilon naught chi E E bar is called as P bar. We name it as P bar, and it is called as polarization density vector. That means this captures the electric fields which is created because of these formation of dipoles. Why? Because of the displacement of the positive and negative charges. So now the positive and negative charges are not in equilibrium. They are not in equilibrium. The equilibrium is lost. And because of that lost in equilibrium, they will start creating the electric fields, and that are put under the umbrella of what we say it as a polarization density vector. Okay. Now, there is one more very important term which is called as dielectric strength of a material, especially in dielectric materials. So the dielectric strength. Now see here, you are applying electric field and you are separating the positive and negative charges. But you know how long a material can withstand an electric field? How long the material can withstand an electric field? Because as your positive and negative charges are separating, and the separation is increasing because of the increase in the magnitude of your applied electric field, the separation will increase. But eventually at one instant of time, this force which is between positive and negative charges will break. That means the electrons will jump out of the orbitals. That means the electrons will jump out of the valence band and becomes free electrons. That means the property of the dielectric material is lost. The dielectric material has now become a conductor because the electrons are now in the conduction band. That means we say that the dielectric material has broken because of the application of the electric field. And what is that electric field value at which this breakdown happens? That is called as dielectric strength. That is, this is the maximum electric field that you can apply for a material. If you just increase a little bit more than this value, then your dielectric material will break down. That means it will no longer be a dielectric, it will be a conductor. Okay, so I think we will stop here, guys, and in the next class we will look at the remaining part of this lecture. Okay, so anything else?
Lecture?